Okay, well, welcome everyone. Today I'm going to be talking about the Apreo. So this version is the higher end version, which does have low vacuum capability. I've been a technician in the CCEM, the Canadian Center for Electron Microscopy, since it started. I've been doing electron microscopy for 40 years, so I have quite a lot of experience with SEM. So the machine we're going to be talking about as Sam said, is less than a year old. We got it installed in January and working in February. So it can be used for a lot of different sort of techniques and sort of getting information on the sample composition, the morphology and surface features, as well as electron crystallography as well. And it does have high and low vacuum settings. So you can see on the microscope itself, you can see our X-ray detector, and over here you can see our EBSD detector for collecting crystallographic information. So we have a lot of components on the system. We'll have the high and low vacuum systems. We have a standard sort of ETD detector. We have a navigation camera and an infrared scope. One of the main things I'm going to be talking about today is the Trinity detection system within the microscope and the different detectors that we have with that. We also do have an insertable backscatter electron detector, which can be used in various modes. The microscope itself does have some different modes of operation, which affect the imaging and working distance you can work it out. It also does have drift compensation, which can help if we're having sort of charging effects. We can also do some stage biasing to help with the landing energy we're using and possibly charging on the system. And we do have a pivot beam system, which can be used for electron channeling contrast imaging. Attached, as I pointed out earlier, we have some Oxford Instruments EDS and EBSD detectors that are fairly high-end and state-of-the-art. So the core of a microscope is its stage. So we do have a nice large stage and plenty of space within the microscope in that we can put samples that might be mounted in plastic, sort of your traditional metallurgical samples, or we can have things on stubs, aluminum stubs, and fit them into the stage here. Or in the case of when we're doing EBSD, we'd remove the main stage and we can put in an apparatus so we can have the samples tilted to 70° for collecting the EBSD data on the phosphor screen and using the force scatter detectors to collect backscatter. We can also have the EDS detector in to also detect X-rays. And here you can see my nice 3D printed bat from Halloween. It's small enough that it fits on the stage, but you can see we can put fairly big sort of objects on. So when we're talking about this particular microscope, we have to sort of consider what sort of interactions we're getting with the sample and what the consequence of those interactions is. So we'll be looking at secondary electrons, backscattered electrons, and X-rays in this microscope. But we have to consider what sort of information we're getting from those particular particles or waves. So in the case of secondary electrons, we're looking at sort of topography and surface. In the case of backscattered electrons, compositional things, topography, crystallography, whether it's doing EBSD or looking at sort of orientation contrast you're getting on things. And with the X-rays, you can get information about the composition, elemental identification, and quantification of the composition. So the newest sort of system we have in some of the microscopes is the Trinity detector system. And that consists of two in-lens detectors. So we have a T1 and a T2. And up in the column, we have a T3 detector. And within the actual lens itself, we also have an acceleration tube, which helps with accelerating the beam downwards, as well as pulling up the electrons for detection as well. So with the T1 detector, it's primarily a backscattered detector, and can detect very low current backscattered electrons. The T3, which is up much higher, detects very low energy secondary electrons. And the T2 does a mix of backscatter and secondary. Now, the pathway we have for the electrons traveling through the microscope, you can see here. So the higher energy backscatter electrons go to the T1 detector, but because of the electric field we have down here, we are actually sort of focusing the secondary electrons into the hole in the backscattered detector. And those are going up and being detected by the T2 detector. It also does get some backscatter as well. It tends to be the higher energy backscatter that go onto the T1. But very low energy secondary electrons, sort of under 2 eV, bypass the T2 detector and go up to the T3 detector. So you can get very low energy secondary imaging with the T3 detector. So we also have different modes within the microscope besides the detectors. So in our sort of standard mode, we can use the traditional Everhart Thornley detector. We have access to the T1 detector, and the T2 is very much functioning usually at longer working distances with not as much signal. So we tend to use it when we're closer up the T2, and the T3 won't be functional at sort of longer working distances. But we can do higher currents in standard mode, so useful for doing EBSD. We would usually depend on, for secondary electron imaging, the traditional detector. And for backscatter, we could use our insertable detector, which fits underneath, or the T1 detector, which is up in the column. Now, in OptiPlan mode, this is where we really use all of the three detectors for doing things. Will tend to be more up in the 10 millimeter or less sort of working distance for doing things. We usually have to have a fairly high landing energy if we're going to be doing any sort of imaging at longer sort of working distances. What happens is the beam gets accelerated by the A tube and decelerated by the electrostatic lens as it's approaching the sample. So it travels through this sort of the system uh, accelerated and then is decelerated for striking the sample. It limits the interactions you actually have with the actual column itself. Now, on the way, we also have immersion, where we can actually make a large magnetic field in combination with the electrostatic lenses to achieve a very small sort of beam size, striking the sample. It tends to be used at very short working distances, but it's sort of our highest resolution in the system. However, we can't look at anything that's magnetic or potentially magnetic due to the danger of it being actually pulled up and hitting the pole piece that we have here. So we can do some energy filtering with the backscatter signal that we're getting on the T1. We have a little compound lens filtering module that can be very useful. But as I was saying before, working distance is important. So when we're thinking about being in immersion or OptiPlan mode, it's sometimes called case use. We have to think about our working distance because it affects what we're actually collecting as a signal. So we can see at longer working distances with the T1, we're getting compositional backscatter. And it's getting a mix of compositional and topography as we're getting closer, around 5 mm working distance. And as we're at close working distances, we're just getting topography from the backscatter uh, uh, signal. In the case of the T2, it's kind of a mixed sort of use detector, so backscatter and secondary. So primarily you'll have a secondary topography. There will be some contribution from backscatter. And as you get to the mid-range, it goes more to a backscatter compositional, and then you're getting more sort of surface sort of detection. And the T3 is basically just surface. So this idea about having a composition, topography, and surface signals is sort of key to the whole microscope. So to help us with this, we have something that does some calculations for us. So we can look at what our landing energy might be. So a mixture of the high voltage we're applying from the gun and any sort of stage bias we're applying. We can then have an estimate of what's going to happen with the different detectors at different sort of working distances that we have here. So the analytical working distance is where we do sort of EDS on the microscope. Optimal will change based on the settings of the microscope, but it tends to be usually for um, the microscope fairly close to the pole piece for doing things. Now we will see some cases where we don't get any sort of signal from the detector. So you'll see this if we go to immersion mode and we don't get anything from the ETD detector. You will also see some limitations on what sort of detection we'll get. So you can see with the T2, it does have this little zone where the detection sort of changes to, as I showed you before, composition. Now, how did this actually work? So here we can see the ETD detector. It's showing up very blue in the detection space. So we're getting a nice sort of topography signal from the thing. So we're at 10,000 times low kV and low current. We're not applying any sort of bias to the stage. And as we look through the detectors, we can see the sort of information we get. So with the T1, we're getting backscatter compositional. So the organic material is showing up very black, whereas the heavier materials are showing up very white or gray or bright gray. We're seeing with the T2, we're sort of getting maybe a little bit of surface and a little bit of, but mostly sort of topography on things. So it's giving us a fairly nice image. And if we look at the T3 detector, we're getting sort of surface effects, so we can see some of the maybe the little fine particles that might be showing up on the surface in various locations. But because we're using very low energy secondary electrons, we can see a little bit of charging effects from the organic material that's on the surface. So we can see some lines and some sort of dark halos from charging. You can play around. We could probably use a little more signal, maybe change the KV a bit, uh, see if we can sort of reduce that, maybe even some stage bias for that. So in cases where we do some stage bias, and yes, you will notice that this is 3000 volts and we're using a 2 kV beam. It's not an equivalent um, reaction, but you can see that if we did go closer with the ETD, we actually wouldn't get any signal from it just because of the bias on the stage sort of deflecting away the primary beam. You can see that it's more of a mixed T1 image. In this case, we're looking at the ETD, so it's a little bit noisy because we do have this sort of stage bias that we're using here. If we look at the T1, we're still getting fairly good contrast with the different things. And we're looking at the T2, it's still looking fairly nice. We can see a little bit of the carbon deposition we're getting on the surface. A little bit more of the charge suppression. We are seeing the surface details a little more clearly now on the detector. So we're having it's sort of a little bit more helpful on things. Now, we also have immersion mode. So in this case, I'm showing an example where we're using the T1 and we're getting sort of topography. But we're using very low currents here, like into the picoamp. So maybe a little bit too low for this image. So it's a bit noisy, but it is giving us very nice topography on the surface of the sample. And we're at a very short working distance, around 3, which is listed as optimal. Here we can see our T2, so we're getting a very nice sort of topographical image. Not as topographical as our T1 image, but we can see a lot of topography on the membrane surface that we're looking at here. And here we're seeing a surface image. So maybe a little bit noisy, maybe need to use a little more current, a little more voltage, but we're able to get up to, 120,000 times with not too much problems. Now our insertable detector, we have 2 modes that we can put it in. We have a concentric backscatter mode where we can have different segments that we can turn on and off or even have inversed in order to sort of adjust the contrast of what we're looking at in the sample. In this case, we're looking at some polycrystalline nickel that's been made by a particular growth process. So we can see all the different twins within the material. So we're getting a lot of orientation contrast. If we look in some of the darker zones, we might even get some dislocations that we can see in the structures. So helpful. Whereas the angular allows you to have sort of a little more angles to things rather than depending on sort of the angle of it being collected. Here you can collect on areas so that you can do things. But the central zone of each detector usually gets you things related more to the compositional sort of a pure sort of compositional signal that we're getting on things. Whereas as you go more off axis, you're going to have a little better sort of topography effects on things. This is a polished sample, so not so pretty for topography sort of effects. Now, we do have low vacuum mode. So you can do some backscatter work in low vacuum. In this case, I am showing, and if I jump back way to the beginning, we have on the stage, which you can see, is a pressure limiting aperture, which through an automated process, it can get loaded onto the bottom of the pole piece here. So with this sort of system, because we can limit the pressure that is going up in the column, we can in the chamber have a fairly high pressure relative to what's up in the pressure up in the column. So we can have a very low vacuum uh, in the actual chamber and a higher vacuum up in the actual column lens system. So if we don't have this pressure limiting aperture on the bottom of the column, we can go up between 10 to 50 pascals in pressure. We can use either water or some sort of auxiliary gas that we connect to the microscope. Um, if we have the pressure limiting aperture and want to work in OptiPlan mode or OptiPlan sort of case use, we can go up to 150 pascals. And in this case, where we're in standard mode, we can run up to 500 pascals. But because we have a lot of gas in the chamber, we have to sort of shorten the working distance to a fairly close sort of working distance here. But you can sort of image the surface of something that isn't coated and traditionally might even melt in the microscope when we're looking at it. So can be very useful for doing material that charges or might be very beam sensitive to things. But it's not really a high resolution mode, especially the more gas that you actually have within the system. We do have a very nice EDS system from Oxford Instruments. So because it is a very large area detector, 170, we can collect a lot of X-rays, which does mean that we can do fairly low energy X-ray work. It also means that we can easily do sort of live chemical imaging. So we can actually collect data as we're looking around the microscope to sort of see the composition of things. So we can have a very low resolution image, but we can do sort of X-ray mapping. We could also do spots and things. If we want to figure out what the composition is in certain areas. So you can have a live update as you move around your sample to figure out, what areas you want to investigate and sort of what might be present on your sample. Um, we can also do the traditional mapping, line scans and points, and we can also combine this with EDS, the EBSD. Over here, we can see some X-ray maps, more sort of traditional static. So here we have a sample that's very tungsten rich with tungsten carbide. So you can see a slight increase in the carbon particles. And surrounding it, we have a nickel alloy. We also have a little boron in the alloy. So, and we also have some silicon, which we didn't do our X-ray map of, but that is there. And we have some iron contamination that's also showing up. So lots of stuff that can be actually done with the EDS. But we can also do EDS in low vacuum. Um, so this can help us if we need to reduce sort of charging effects on the electron beam and also the backscattered and secondary electrons that we're using for imaging. We do have the skirting effect to deal with, which happens when you do have an atmosphere, that you do tend to get the electrons sort of spreading out a little bit more over the surface of the sample rather than being at the point or interaction volume where you are. It doesn't cause a lot of problems for imaging. You just don't get as nice high resolution image. Maybe a little more noise than you would normally would get uh, with high vacuum mode. But in EDS, it does cause the problem that you will get some X-rays that are not necessarily local to where you're scanning. So you may detect features that are remote from where you're looking, up to many microns from where you are. So have to be careful about that in how you interpret things. But you can see on the map that we have here that we can see fairly well that, different elements are sort of distributing out on things. The other thing with this map, it's also a montage. So this actually consists of about 25 individual maps being combined together in a montage. So another thing that we can do with the EDS software and with the sort of automation we can do within the microscope. We also have an EBSD detector. So on crystalline materials, we can gather a wide variety of different information. So we can do a lot of stuff with the microscope that allows us to sort of identify phases, quantify phases, though you will have some issues with phase quantification because unlike X-ray diffraction, we're collecting from sort of a very surface, sort of 10 to 50 nanometers of the surface. So it doesn't necessarily give you an accurate sort of snapshot. And you may also have polishing effects, which affect the sort of quantification of things. Can be useful for crystal texture. So if you're doing things that are rolled or thermomechanically processed, you can have a look at the textures, pole figures, inverse pole figures, grain size, and other sort of grain parameters. You can have a look at the parent grain size. So in the case of materials which do have a sort of prior structure that exists at higher temperatures, you can have a look for evidence of the prior grain size, like sort of in steel, sort of the austenite grain size. You can look at the boundaries, so between grains, twins, and phases. You can do some dislocation analysis. We do have a fairly high resolution camera, so you can also do high resolution EBSD, collect the patterns if you want to do pattern analysis in a program. You'll have to supply the program though. Can be very useful, especially if you're looking, doing a little bit of dislocation analysis or looking at sort of strain within materials. There are programs out there that you can take the patterns and do sort of further refinement of the patterns to identify things better. So some of that software is starting to be included in the EBSD software for an additional price by the companies. So that can be sort of very useful on things. The microscope gets used a lot for EBSD. So it tends to be sort of the main sort of expertise I usually have. But we do have automation of things. So Thermo Fisher, the parent company that makes the microscope, does have a program called MAPS, which allows you to make sort of large mosaics of objects you might be looking at. So do mapping. We don't have ChemiSem on this particular microscope. It is on a Quattro. You can also combine that in to do sort of EDS with Thermo Fisher's MAPS program. But in this case, we usually use the Oxford software if we want to combine the mapping of the images with either EDS or EBSD or both of them. Though EBSD can be a little bit challenging because we do have the sample tilted to 70 degrees for things. You can import a reference image into both these programs if you want to look at other data and refer it to where you're doing the other types of analysis or imaging. Something we're working on, which is relatively new for us, is electron channeling contrast imaging. We were able to do it in the previous microscope, but it didn't get very much use. We are sort of looking at this more and trying to develop sort of protocols and techniques for doing it properly. But it can be very useful for looking at the dislocation structures in materials. You can also do that to some degree with EBSD. So, collect an EBSD pattern. You can use the force scattered detectors from the EBSD detector and collect sort of images. But basically the pattern we're getting with electron channeling is similar to the Kikuchi pattern. And we try to center along the band or reflector that represents the dislocation structure that we're looking for or the structure of the material. What we haven't been able to do before is actually rock the beam so that we can actually collect the data off a tilted specimen. We wouldn't have it at 7 millimeters on our particular system. It's 10 millimeters. And we only have 5-axis tilting. If you have a fib, you can do 6-axis tilting, or if you have a fib stage in your SCM, you can do 6-axis tilting, which would be an advantage. But you can also do some imaging of, say, the EBSD sample with the force scattered detectors, and you can get sort of images that will show you the electron channeling contrast imaging. Though in polycrystalline materials, you have to look for particularly dark sort of grains so that you get the sort of contrast to actually see the dislocation structures within them. So you can look at all sorts of different types of dislocations in the microscope. And that is the end of my brief sort of summary of what I was talking about. So I want to thank you for attending. There's lots of time for questions. And here you can see one of the samples that we test the students on for doing SEM.